the sun or any typical incandescent bulb in your home releases white light. White light is a light of all of the different visible colors within the visible spectrum. It has the entire rainbow included within it. So that when this white light goes through a prism, you can actually see there are all of those different colors coming from the sun. But you can also study individual elements in lamps which show not an entire visible spectrum. For example, potassium, when it releases its light, it really just releases two different colors, violet and orange, in these thin spectral lines. Hydrogen, it releases only these four thin spectral lines. These kind of fingerprints belong to each element. Every element has a specific fingerprint. In fact, because different elements have these different atomic emission spectra, we can evaluate what elements are in certain stars by the forms of light that come out, the wavelengths of whatever certain thin lines come out. But yes, you can see that hydrogen, which is our focus today, has only these four visible spectral lines. Now, this spectral, this atomic emission spectra, which was first measured by Balmer in about 1850, was actually the source for Bohr's description of the hydrogen atom and the energies of the electrons. You see that you have different energies of light coming out because you have different wavelengths and frequencies, because there are different energy transitions that hydrogen's electrons have around the nucleus. You see, there are those four different energies of transition, as you can see here, going from around hydrogen, principal energy level 6 to principal energy level 2, 5 to 2, 4 to 2, 3 to 2. And having these different drops in energy, there are different energies of released light. The light that you see coming from a hydrogen lamp. Now, I guess it's most important to realize that a drop of 3 to 2 has less energy than a drop of 4 to 2, or 5 to 2, or 6 to 2. So having less energy is released. The light has less energy. It's longer in wavelength. It's red compared to the higher energy transitions. A transition of 6 to 2 gives the highest form of energy, visible light, violet. Now, what if you had a drop of even greater distance? A drop of say 7 to 1, or 6 to 1, 5 to 1, etc., etc. You would have even more energy released than these transitions to n is equal to 2. And releasing even more energy than that violet visible light, you would have ultraviolet light. Whereas transitions to n is equal to 3 or higher, these have less energy released than the transitions to n is equal to 2. And therefore, having less energy than the red within the visible spectrum, those are infrared transitions. We can see that there are many different possibilities of transition of an electron around the hydrogen atom. 4 of those possibilities are visible in visible light in terms of the energy released, but the other possibilities are ultraviolet, infrared, or even less energy. Yes, an electron most normally exists in that lowest energy state, n is equal to 1 on hydrogen, but sometimes it's not going to be in the ground state, but is in higher energy states, when an electron is higher than Aufbau's principle would suggest. These are called excited states, when an electron is higher in energy than its ground state, where it might normally exist. Now, we can do calculations. This only applies to AP and college level students. We can do calculations for the electron around a hydrogen atom using Rydberg's constant. Yes, the energy of an electron in its position around a hydrogen atom is equal to negative Rydberg's constant, which is 2.18 times 10 to the negative 18 joules, times 1 over n squared, where n is the principal energy level that the electron is in. And so we can calculate for the energy change in an electron as it transitioned, and therefore the energy absorbed or released when the electron transitions. The change in the energy of the electron is equal to the final energy minus the initial energy, or replacing those energies with Rydberg's constant times 1 over n squared, we get the following. And then from this we can derive the following equation. This is the equation to tell us how much energy is absorbed or released when we have a certain transition from Ni to Nf, where I is the initial principal energy level, and F is the final principal energy level of the electron around the nucleus. So you can calculate for the change in energy, and therefore how much, what the frequency of the light released or absorbed is, and therefore the wavelength. For example, say you wanted to determine the wavelength of light released when an electron falls from hydrogens, n is equal to 4 principal energy level 2, and the n is equal to 2 principal energy level. Okay, so first we should recognize that as the electron falls, it goes from a high energy state to a low energy state. It's losing energy, which means energy is going to be released when that transition occurs. But if an electron were to transition from 2 to 4, to gain energy, that would only occur by the electron absorbing energy from light. Okay, so we know the certain transition, Ni and Nf. We can therefore know, using the following equation, the change in the energy of the electron, and therefore the energy of the photon emitted, and having energy of a photon is equal to Planck's constant times frequency, we can calculate for frequency, and then having frequency, and knowing the speed of light, we can calculate for the wavelength of that light. You would find that transition from 4 to 2 should give you visible. Transitions which fall to principal energy level 2 usually give you visible light, as you can see with this blue-violet light for this, actually 4 to 2 for this blue-green light. Thanks for watching, guys.